Hello everyone, I am Anwoy and I will be presenting our work titled POSIX, a prompt sensitivity index for large language models. This work has been accepted at the findings of the EMNLP 2024. This is a result of the collaboration between IIT Delhi and Media and Data Science Research Lab of Adobe India. I'll be presenting this work on behalf of my co-authors, Kowndinya and Sumit from Adobe and Professor Tanmoy from IIT Delhi. So we are all, I guess, using LLMs for our various day-to-day tasks, from drafting emails to, say, writing some basic code or something like that. But with this use of LLMs, this prompt engineering has become a very crucial thing. I would like to call it the dark art because we actually don't understand which prompt works and why it works and things like that. This actually uh, remembers me of the scene in Harry Potter's and the Philosopher's Stone when Hermione actually tells Ron that how to actually pronounce the spell Wingardium Leviosa, which actually makes objects float, and she tells it's Leviosa, not Leviosa. So the emphasis is on O and not S. So though the spell is the same, how we'll pronounce it actually actually decides how its outcome would be. And we see a similar things with LLMs. Even if we give almost similar prompts where our intents are the same, a slight variation in the wordings of the prompt actually changes the output a lot. For example, I was playing with Llama 3 8 billion instruct model, and I asked it, "Are you familiar with the principles of Buddhism?" And it gives me an answer, yes, I am familiar with the principles of Buddhism. Buddhism is a spiritual practice originating in India. Actually, I tweaked it a little bit and asked, how much do you understand Buddhism? And suddenly, I don't know why, it becomes sarcastic, saying 0.01%. Just kidding, I am not a Buddhist scholar either. So look, my intent when I ask those questions, are you familiar with Buddhism and how much do you understand Buddhism, is the same. I want to see some information about Buddhism, what LLM can tell me about Buddhism. But it looks as if just paraphrasing it, changing the wordings a little bit here and there actually makes a whole lot of difference. But when LLMs are released nowadays by different organizations, and they come up with a model card, what the report are basically the accuracy numbers or the performance measures on various popular benchmarks like MMLU, GSM8K, math, and things like that. But the question I would like to ask is accuracy enough? Does accuracy tell the whole story? When you are saying that you need prompt engineering to make LLMs work, then for even for these accuracies, you must have done a lot of engineering and prompt template stuff, right? So accuracy doesn't tell the whole story. Of course, accuracy, or but for that matter, any measure of correctness on different benchmarks is important, but it doesn't tell the whole story. If your LLM is very much sensitive to the prompts you give, maybe in real world use cases, it's tough for the users to use it. Normal users like us in day to day life use cases, like say drafting an email and stuff like that, we don't prompt engineer. And if it depends on the tone of the prompt or the wordings of the prompt, it may be a difficult choice to make. So, but we see that there is no standard measure for capturing prompt sensitivity. But one more thing I would like to emphasize, its sensitivity as a property is orthogonal to correctness. What I mean to say is an LLM can be always incorrect and still it can be very robust. For example, suppose I ask an LLM, what is the capital of India? Say, for every variations of the prompt, it always says hello. So I ask it, what is the capital of India? It says hello. I says, can you tell me the capital city of India? It says hello. I ask it, can you tell me which city serves as the capital of the country India? It says hello. Yes, it is always wrong. The capital of India is New Delhi. But it seems as if the LLM is not at all sensitive. Rather, it is very robust to the variations in prompts. Correct? But such LLM is of course not useful if it is always wrong. So maybe a good thing would be to take accuracy and sensitivity together, and that can tell maybe a bigger part of the story. For example, suppose we have two models, model A and model B, where model A performs 85% on a benchmark of interest. So compared to model B, which says it performs has an accuracy of 80%. So model A has a better performance on the benchmark. But suppose model B is less prompt sensitive. In fact, say model A is 0.6 sensitive. That means, say from an index of 0 to 1, its sensitivity is 0.6. So it is very sensitive. And model B is comparatively very less sensitive and it's more robust. So in such a case, from a user-centric perspective, when we see that the performance on a benchmark is comparable, I would prefer to go with model B for our use case when deployed in a basic user-centric environment. So but for this we need a sensitivity measure. So we need a holistic measure which can capture the prompt sensitivity of an LLM, and that would actually make the evaluation LLMs more comprehensive, right? So accuracy doesn't tell the whole story. So here is where our metric comes in. We introduce POSIX, which is basically a novel prompt sensitivity index, which is actually doesn't consider the correctness of the input. It considers the variations in the input, which we will see. And it's easy to use. You can just pip install prompt sensitivity index and use it for the evaluation of your LLM or for your use case. You'd urge the organizations that when you release, please also release the POSIX score so that we can make a more informed choice whether your LLM is suitable for our use case or not. Of course, you release the accuracy, but please also release the sensitivity index, right? So you can check out our GitHub repo in this QR code. So now let's look at the problem statement. So given a prompt along with its intent preserving variations, which I'll discuss in the upcoming slide, what we mean by intent preserving variations. So if you have a prompt and it intent preserving variations, how do you measure the sensitivity of the LLM on the given set of prompts? Two things to keep in mind. Whatever measure we design, it should work on all variation types, say paraphrasing, tone, grammatical errors. These kind of variations may occur within prompts, and it should work on all types of tasks. It can be open-ended generation task, it can be MCQ question answering, it can be a classification task, it can be a reasoning task. It should work on all kind of tasks. Now, what do you mean by intent preserving prompt variations? Suppose, as I was giving an example, what is the capital of India? There can be several variations of this prompt. What city serves as the capital of India? Can you tell me the capital city of India? Where is the capital of India located? In all of these prompts, the user expects the similar response. So we call these kind of prompts in which the user actually are expecting the similar response, only there are variations in the wordings, or maybe there are some spelling variations or things like that as the intent preserving variants, right? Now let's look into what should a sensitivity measure capture. What kind of differences in the outputs actually tells you that the model is sensitive to prompt variations? First thing is response diversity. Response diversity actually means, suppose you have a prompt and you have n intent preserving variations of it. So for this n+1 prompts which are actually asking the similar question, the user is expecting the similar answer, how many unique responses does the LLM give? For example, your model A, which is Llama 3 8 billion instruct model, and model B is Mistral 7 million instruct model, he asks the question, what is the capital city of India? And along with its variations, like, so the first question is, what is the capital of India? The second question is, which city serves as the capital city of India? The third question is, where is the capital of India located? And things like that. So when we give 1, 2, 3, 4, 5 intent preserving variations of this same prompt, what is the capital of India? Llama 3 8 billion provides 5 unique responses. That is, for every 5 variations, it gives a new answer. It comes up with a new answer. Though it says New Delhi, but the way it presents its answer and the information it gives is very different. For example, just look at this fourth variation where it generates New Delhi, and then it starts generating another new question, which is the following is the largest state in India. Whereas, say, in the first example, it gives an explanation as to why New Delhi, where it is located, and things like that. Whereas when you ask Mixtel 7 million instruct, out of 5 times, uh, 4 times it says New Delhi, and 1 time, I don't know why, but it generates options for the question, interestingly. So in this case, clearly model A, which is Llama 3, is more sensitive to the prompt variations, right? Second thing is response distribution entropy. Suppose for the two models, model A and model B, the number of unique responses it produces is the same. Then how do you measure the sensitivity? We look at the frequency of the number of unique responses, right? So if we look at the frequency of the number of responses, it will give a kind of distribution, frequency distribution over the unique responses it produced, and higher the entropy, higher the sensitivity. For example, in case of this example, say in model A has a lower entropy. It is more likely to produce this green response, which is A basically, option A basically. But model B is an equal frequency of producing each unique response. Clearly, model B has a higher entropy and it is more sensitive. The third factor is, suppose you have a similar frequency of unique responses and similar number of unique responses, and how do you check whether what is the sensitivity in two models? Then there comes the semantic coherence. What semantic coherence captures is it's basically looks at the semantic similarity between the generated responses. So lower the semantic similarity, that is, responses are very different in meaning, that means the sensitivity is higher. And fourth thing, when all other aspects are same, your semantic similarities are almost the same, your number of responses is the same, your frequency of the number of unique responses is the same, then we look into variance in confidence, that is how the probability of the responses actually varies. So the higher variance in the log likelihood of the same response actually results in higher sensitivity. So a measure which is holistic in capturing sensitivity is independent of the correctness of the responses, rather is dependent on these four aspects of the outputs of this intent preserving set of prompts, right? So what do you propose? What is our primary assumption? Suppose there are two intent preserving variation of prompts, and for one we get this response star, for the other we get this response triangle. So probability of the star given the form 1 of the prompt should be approximately equal to probability of the star given the second form of the prompt. So this form 1 of the prompt, what is the capital of India, and form 2 of the prompt, can you tell me the capital city of India, actually resonates the same intent of the user. So the probability of a particular response star should be same, even should be almost the same, even if we alter these prompts. So basically we would want the LLM to capture the intent the user is actually trying to convey through the prompt, and not go into the specificities like the wordings used or things like that, right? So this is where our sensitivity index comes in. So suppose we were set D a model M and X is an intent aligned prompt set. So for every prompt Xi in X, we have the corresponding response Yi. So we define the sensitivity of model M on the intent aligned prompt set X as the summation of the ratio of the log probabilities, right? So basically it's the log of the ratio of probabilities of a response if we change the input prompt. So basically this log p of yj given xi upon p of yj given xj captures the relative change in the likelihood for generating a particular response yj upon replacing the input prompt by one of its intent preserving variant. We normalize it by Lyj, which is the length of the response, the number of tokens in the response. So this is basically to accommodate arbitrary response length. So this doesn't blow up with the number of tokens generated. The POSIX score on a data set or a benchmark D is an average of the sensitivity scores on the internal line prompt sets corresponding to every prompt. Now we empirically show that POSIX actually captures all those four aspects we discussed previously. It increases with the number of unique responses. It increases exponentially with the response distribution entropy. It decreases with the increase in average cosine similarity, and it also increases linearly with the increase in probability variance, log probability variance basically. So empirically we show that it does capture all these four aspects and is a more holistic measure. Now, what observations do you make using POSIX? To give a brief overview of the experimental setup, we use 8 LLMs, 4 families, Llama 2, Llama 3, Mistral 7B, Olmo 7B, along with their base and instruct versions. 3 benchmarks we test on: MMLU for MCQ tasks, Alpaca for open-ended questions, and Big Bench Hard for reasoning type questions. We generate 60 variations of each prompt. For each prompt, we generate 60 variations, where 20 variations come from each of the 3 categories. First thing is spelling errors. That is, for the original prompt, we do random perturbation with inserting certain characters in random words, omission, transposition, substitution. We vary the prompt templates. We have 20 different prompt templates with their options and enumeration remaining same in MCQ, so that it doesn't vary in the gold response. We take 20 paraphrases generated using GPT 3.5 and checked manually for correctness of the paraphrases. And we also use a mixture where we have 20 variations sampled randomly and uniformly from each of those 3 categories. Now let's see some of the results. So first question we ask, what is the effect of instruction tuning on sensitivity? Does instruction tuning always reduce the sensitivity? It turns out no. For example, in MMLU, when you change the templates of the input prompt, we see base is more sensitive than chat. But then in open-ended generation, we see chat models are more sensitive. So, so the same thing is shown in this numerical plots, where you can see that in MMLU, say, Llama to base is more sensitive than Llama to chat. But then for open-ended, you say Llama to chat is more sensitive, and similarly follows in, say, Olmo or say Llama 3. But these chat models are actually both instruction tuned and RLHF'd. So we separately trained the Llama 2 and Mistral 7 billion models on FLAN, just fine-tuned, so to disentangle the effect of this human alignment. And we see a similar story, and except in prompt templates, generally chat models are less sensitive than our custom fine-tuned models, instruction fine-tuned models. But in prompt templates, we see these FLAN-tuned models are kind of much less sensitive than the chat models. This can be due to the case that FLAN consists of MCQs, MMLU consists of MCQs, so that there can be this help from tuning only on FAN, right? Then we ask the question, what's the impact on model scale? Does larger models are always less sensitive? It turns out no. At MMLU, for example, Olmo 7B shows a much higher sensitivity than Olmo 1B. Though the accuracy of Olmo 7B on MMLU is better than 1B, the sensitivity for 7B is higher. So this shows that the sensitivity doesn't necessarily decrease with model scale, increasing the model scale, and also shows that accuracy and sensitivity are completely different aspects. You also test with Llama 2 7 billion and 13 billion base and chat models to check the effect of increase in parameters, and this is tells a similar story. The 13B model is not always lesser sensitive than 7B model. We can say that increase in parameter count doesn't necessarily decrease sensitivity. But in case of few short examples, we see adding few short examples, even if it's just one, can significantly reduce prompt sensitivity. For example, when you add even a one example, the sensitivity drops significantly in case of Llama 2 and both Llama 2 and Mistral models. You can see that. However, adding more shots doesn't always make some that significant gains in decrease in sensitivity. So the decrease in sensitivity from 0 shot to 1 shot is significantly higher compared to say 1 shot to 2 shot or 2 shot to 3 shot. Now, the impact of variation categories. We see that for MCQs, prompt template is the most sensitive variation type. Whereas for open-ended questions, the way you ask the question, the wordings, the paraphrasing, the how you phrase the question is very important. So if you are really doing this dark cut of prompt engineering, and if your question is a multiple choice question, maybe you should look at finding the proper template. If your question is open-ended question, maybe you should look into how you phrase the query. Okay, so if there is one take-home message I would like to give is LLM evaluations are incomplete. Try POSIX. It's very easy. Go just pip install prompt sensitivity index and do check out our paper and code. Thanks.